First, introduction. Its definition is Newton's law of cooling or warming states that the rate of change of the temperature of a body is proportional to the difference between the body temperature and the temperature of the surrounding medium.
The formula we use for the cooling and warming problem is Newton law formula, which is dt over dt equal to k multiplied with t minus ts, where k is constant and dt stands for temperature of the object for t bigger than 0, and lastly ts stands for the temperature of the medium around the object. Question 1. A bowl of tomato soup at 156 Fahrenheit is placed in a room of temperature 60 Fahrenheit. 3 minutes later, the soup has cooled to 123 Fahrenheit. If the temperature of the soup obeys Newton's law of cooling, when will the temperature reach 90 Fahrenheit? How to solve? First, we will use the information Ts equal to 60, and we will use the Newton law formula to calculate this problem. Then we will make the capital T for the subject. Next, we will integrate both sides. Then we will get ln T minus 60 equal to Tt plus C. After that, we will put exponent at the both sides to eliminate ln. At the end, we will get Tt equal to Ce the power of Kt plus 6. Next information is T equal to 0 and the temperature when the time is 0 equal to 156 Fahrenheit. And we will substitute all this information into the current equation. Then we will get C equal to 96. Therefore, the current equation is T equal to 96 in the power of Kt plus 60. Then we will use another information, which is T equal to 3 and the temperature when the time is 3 equal to 123 Fahrenheit. Next, we will substitute all this information to the previous equation. Then we will get 123 minus 60 equal to 96 exponent the power of 3k. Then we will put ln at the both sides to eliminate exponent. Therefore, we will get k equal to minus 0.140404458. And lastly, we will substitute the k into the previous equation. Then we will get, for the current equation is Tt equal to 96 e the power of negative 0.140404458 t plus 60. Lastly, the question wants us to find at what time the temperature is 90 Fahrenheit. So we will use the previous equation that we get from the previous calculation, and we will substitute the temperature 90 Fahrenheit into the previous equation. Then we will get 90 minus 60 equal to 96 e the power of minus 0.140404458. Then we will put ln at the both sides to eliminate exponent. Lastly, we will get the time when the temperature T equal to 90 Fahrenheit is 8.284286885 minutes.
Question 2. The cooking started at 12:30 p.m. and it took about 30 minutes to fully grill a meat, and the meat was put aside. The surrounding temperature is 90.5 Fahrenheit. The temperature of the meat is 157.1 Fahrenheit as soon as the meat is done. After 15 minutes, the temperature of the meat is 120.5 Fahrenheit. If the meat can be eaten at 100 Fahrenheit, then at what time can they eat? How to solve? The information given, first we put it into the general formulas. So we got T equal to A exponent power of KT plus 90.5. Then we can find A. First, we replace T as 0 value. So T0 equal to A exponent power of K multiply 0 plus 90.5. Then T0 is the same value as 157.1 equal to A exponent power of 0 plus 90.5. Next, 90.5, bring it to the other side. So A multiply 1 equal to 157.1 minus 90.5. So we got the answer for A, 66.6. So we got a new value for T. T equal to 66.6 exponent power of KT plus 90.5. Next, we replace T as 15. So T15 equal to 66.6 exponent power of K multiply 15 plus 90.5. Then T15 is same as 120.5. So 120.5 equals to 66.6 exponent power of 15K plus 90.5. We bring 90.5 to the other side, so 66.6 exponent power of 15K equals to 120.5 minus 90.5. So we got 66.6 exponent 15K equal to 30. cancel exponent, we put ln both sides. So ln exponent power of 15k equal to ln 30 divided by 66.6. Then we cancel out the ln. So 15k equals to ln 30 divided by 66.6. Then we can calculate for the value of k. K equal to negative 0.0532. So we got the new value for our t. T equal to 66.6 exponent power of negative 0.0532 t plus 90.5. Next, we want to find value of t. Tt equal to 100. 100 equal to 66.6 exponent power of negative 0.0532 t plus 90.5. We bring 90.5 to the other side. So 66.6 exponent power of negative 0.0532 t plus equals to 100 minus 90.5. 66.6 exponent negative 0.0532 t equal to 9.5. Next, we want to cancel the exponents. So we put ln both sides. So ln exponent power of negative 0.0532 t equal to ln 9.5 divided by 66.6. So cancel the ln, we got negative 0.0532 t equal to ln 9.5 divided by 66.6. So we got the value for t equal to 36.58. Then we change it to minutes and seconds. So the answer is t equal to 36 minutes. And last one is the time the meat can be eaten. So 12:30 p.m. plus 30 minutes fully grilled time of the meats plus 30 minutes to cool down the meats. So we got the answer of 1:36 p.m. that the meat can be eaten at 100 Fahrenheit.
Now we move on to question 3. A murder victim's body was discovered at midnight and the temperature of the body was 30 degrees Celsius. 1 hour later, the temperature of the body was 27 degrees. Assume that the air temperature remains constant at 20 degrees. Calculate the victim's time of death if the normal body temperature is 37 degrees Celsius.
How to solve the question? First thing first, we have to use the general formula, which is d temperature over d time equal to k in bracket t minus ts, which is ts is the temperature surrounding. After that, we put t time and t minus ts to opposite sides, and it will become d temperature over t minus ts equal to k dt. Then we have to integrate both sides, and lastly, we will get ln t minus 20, which is the value of temperature surrounding, equal to kt plus c. Next, we put exponent for both sides, and it will become e ln t minus 20 equal to e kt plus c. For left hand side, which is e ln t minus 20, the exponent and ln will cancel out each other, and we will only left with t minus 20. For right hand side, which is e kt plus c, we have to separate them first, and it will become e kt multiplied by e c. And we will get c exponent to the power of kt. And lastly, we will get our first equation, which is t in bracket time equal to c e kt plus 20. Now we need to find the value of c. From the question, we already have our next information, which is when the time is 0, the temperature of the body was 30. So we need to replace t in bracket t equal to 30, and the time we have to replace it by 0. And that is how we will get our value of c, which is 10. This is our second equation, which is t in the bracket t time is equal to 10e to the power of kt plus 20. Moving on to the next step, now we want to find the value of k. We use the information, which is when the time is 1, the body temperature is 27, and we use the same step as before, which is we will replace the value of t and equal it to 27. Then we do ln to both sides to get rid of exponent, and that is how we will get our k value, which is negative 0.3566. We replace the value of k to the equation from before, and the latest equation is t in bracket time equal to 10e to the power of negative 0.3566 t plus 20. We want to find the victim's time of death, assuming that the normal body temperature is 37. So we use our equation, which is 10 exponent to the power of negative 0.3566 t plus 20. Then we move the value of 20 and 10 to the opposite sides, and it will become 17 over 10 equal to exponent to the power of negative 0.3556 t. Now we only want the value of t, which is the same as before. We have to eliminate exponent from the equation. So we put ln to both sides, and that is how we will get the value 0.5306 equal to negative 0.3566 t. Then to find the value of t, we do a quick division, and that is how lastly we'll get the time equal to negative 1.49 hours. For the victim's time of death, we have to remember that the body was found at midnight, which means it was found at 12 AM. So the value of time is negative 1.49, and we assume it to be approximately negative 2 hours. It means that the victim's time of death was 2 hours before it was found. So 12 AM, we minus with 2 hours, and then we will get 10 PM. 10 PM is the time of death for the victim.
In conclusion, the first order differential equations such as Newton's law, cooling and warming can be of great help in our real life. This can be proved when we use this law to find specific time or specific temperature in many situations.